Let's assume that E is a set of cardinality n, which means that it has n members. We would like to show that the sum among all subset A and B of E, the sum of the cardinality of the union of A and B, is equal to 3n multiplied by 4 to the power of n minus 1. So to start with this problem and to give a quick reminder to those that might not know exactly what cardinality means, let's imagine that you have a set E that contains 3 elements, let's call them A, B, and C. Then the cardinality of E is simply the number of this element. So the cardinality of E will be equal to 3. Now, another fact that is well known in set theory and combinatorial mathematics is the cardinality of the power set. So what we call the power set P of E is simply the number of different subsets that E can contain. So P of E can contain, in that case, the empty set, but also the singleton A, the singleton B, C, but we can also have A and B, B and C, A and C, and finally the complete set A, B, and C. So if we count all of these subsets, we notice that we have 1, 2, 3, 4, 5, 6, 7, 8. The cardinality of the power set is equal to 8, which is 2 to the power 3. And it's actually not a coincidence, it's a well-known fact that the cardinality of the power set is equal to 2 to the power of the cardinality of the set itself. And we have this relationship because if you imagine that you have a set that contains n elements, so we are going to write this element 1, 2, up to n, then there is 2 possibilities for the first element to belong or not to the subset A. So there is 2 choice for the number 2, etc., up to the number n that has 2 choice. So the number of choice will be equal to 2 to the power of n. So there are exactly 2 to the power of n possible subset of a set E. So we can write as a reminder that the cardinality of the power set E is equal to 2 to the power of n. Now, before demonstrating the result above, an interesting intermediary result is the following one. So we would like to obtain a formula for the sum for all subset of E of the cardinality of A. And the way we are going to solve this sum is to partition this sum according to the cardinality of each subset A. So we have this is equal for the sum for k equal 0 to n of the sum of all subset A that have a cardinality equal to k of the cardinality of A. And because by definition the cardinality of A is equal to k, we can replace this by k in this sum, and we can move this k on the other side of the sum. So we have the sum from k equal 0 to n of k sum of 1 for all the subset A that have a cardinality of k. And now what this sum is doing, it's actually counting the number of subset A that have a cardinality exactly equal to k. And so what is this number equal to? Well, we know that the number of ways to choose k elements among a set of n elements is exactly equal to n choose k. So this sum is equal to the sum from k equals 0 to n of k multiplied by n choose k. Okay, great. Now let's see how we can simplify this sum. So first of all, we notice that we can perfectly start the sum from k equal 1 instead of 0. And this is because when k equals 0, this element will just disappear because it will be equal to 0. And so we will start this sum from k equal 1, and then we are going to develop the n choose k. So we have sum from k equal 1 to n of k multiplied by factorial of n divided by factorial of k multiplied by factorial of n minus k. Here what we can notice is that we have a k on the numerator and the denominator, and we know that k divided by the factorial of k will be equal to 1 divided by the factorial of k minus 1. And we can also notice that n minus k is equal to n minus 1 minus k minus 1. So this is equal to the sum from k equal 1 to n of n factorial of n minus 1 divided by the factorial of k minus 1 and the factorial of n minus 1 minus k minus 1. So this is equal to n multiplied by the sum from k equal 1 to n of n minus 1 choose k minus 1. Here what we can do is to use the change of indice p equal k minus 1, and we have n sum from p equals 0 to n minus 1 of n minus 1 choose p. And according to the binomial theorem, we know what this sum is equal to, and this is equal to 1 plus 1 to the power of n minus 1. So, in other words, we have this sum, the sum of all subset A of E of the cardinality of A, that is equal to n multiplied by 2 to the power of n minus 1. Okay, so now let's find another interesting formula that is about the intersection of two subsets A and B. So we would like to know the sum for A and B being subset of E of the cardinality of the intersection of A and B. To solve this, we're going to use the same trick as before, which is to partition this sum according to the cardinality of the intersection of A and B. So this sum is equal to the sum for k equals 0 to n of the sum for all intersection A and B that has a cardinality of k of the cardinality of the intersection A and B. And because again, by definition, we say that this cardinality is equal to k, we have the sum from k equals 0 to n of k multiplied by the sum of 1 for all the intersection A and B that have a cardinality of k. So the goal here is to identify the number of subset A and B whose intersection has a cardinality exactly equal to k. So to identify this number, we'll have to think a bit in reverse. And what I mean is that generally when we talk about intersection of two subsets, what we do is that we start with a set E that has a cardinality of n. Then we define a subset A that is here. And then we will define a subset B that is there. And then we will find their intersection as being this part, and we can calculate the number of elements in that intersection. Here the reasoning will be slightly different because we will start with this intersection. So we will start with a subset that we will call intersection of A and B that contain k elements, and then we are going to find how we can add some element in B that do not belong to A and how to add some element of A that do not belong to B, so we can find all the subset whose intersection has a cardinality exactly equal to k. So the first step is to choose k element among n elements, and as we have seen above, this number of choice is equal to n choose k. And now that we have chosen this k element, we need to find p element outside of this k element because we want them outside of the intersection. And the number p can be anything between 0 and n minus k. So in other words, the number of choice is equal to sum for p equals 0 to n minus k of n minus k, choose p. And now remain the choice for the other subset that, in that case, should be outside of the k element we have chosen and also outside of the p other elements that we have chosen. So the number of choice in that case is equal to n minus k minus p, but we can take any number of elements q as long as they are outside of this n minus k minus p already chosen element. So in that case, the choice is equal to sum for q is equal to 0 to n minus k minus p of n minus k minus p choose q. And we know that this sum, again, according to the binomial theorem, is exactly equal to 2 to the power of n minus k minus p. So, in other words, this sum is equal to n choose k sum from p equals 0 to n minus k of n minus k choose p 2 to the power of n minus k minus p. So as a quick reminder here we have the number of choice of intersection that have a cardinality of k element. Here what we have is the number of way to choose the subset A, and here what we have is the number of way to choose the subset B. Notice that we can apply the binomial theorem one more time, and this quantity is exactly equal to 1 plus 2 to the power of n minus k. So in other words, this is equal to n choose k 3 to the power of n minus k. So we can write that this sum is equal to the sum from k equals 0 to n of k n choose k 3 to the power of n minus k. Notice that we can use the same trick we used above for k multiplied by n choose k. We know that each element will be equal to n multiplied by n minus 1 choose k minus 1. And we just have to start the sum from k equal 1. So this is equal to the sum from k equals 1 to n of n minus 1 choose k minus 1 3 to the power of n minus k. By change of index k, we have this that is equal to n multiplied by the sum from k equals 0 to n minus 1 of n minus 1 choose k multiplied by 3 to the power of n minus 1 minus k. And by applying the binomial theorem one more time, we have n multiplied by 4 to the power of n minus 1. Okay, so now you can tell me, okay, great, Q, you found what was this equality equal to when we have the intersection over here, but the initial formula was about the union, not the intersection. Well, this is true, but now the good thing is that we have two ways to solve the initial formula, and one way is actually to use the intersection, and the other way that use the union will still work, but will actually be a bit more difficult. So the trick we are going to use is the following one. We're going to write this fundamental equality, that is that the cardinality of the union of two subsets A and B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection. And this is going to be super useful because if we use this equality inside the sum, we have that the sum for any subset A and B of E of the cardinality of the union A and B, this is equal to the same sum, but of this formula, so we have A plus B minus the cardinality of the intersection of A and B, which is equal to the sum for the subset A and B of the cardinality of A, plus the sum for A and B of the cardinality of B, minus the sum for A and B of the cardinality of the intersection A and B. By symmetry, you can notice that these two quantities are exactly the same, so this is equivalent to counting this quantity twice, and we have 2 times the sum for A and B of the cardinality of A minus the sum for A and B of the cardinality of the intersection. Now we note that the sum for all subset A and B of the cardinality of A is exactly like writing the sum for all subset B of the sum for all subset A of the cardinality of A. We have seen previously that the sum for all subset A of the cardinality of A is equal to n2 to the power of n minus 1. And then let's not forget that we are counting this quantity for all subset of B, and we know that there are 2 to the power of n of them. So at the end, this is equal to 2 to the power of n multiplied by n, 2 to the power of n minus 1. We also just calculated that this quantity was equal to n multiplied by 4 to the power of n minus 1. So at the end, we have 2 multiplied by 2 to the power of n multiplied by n multiplied by 2 to the power of n minus 1 minus n 4 to the power of n minus 1. This can be simplified by n multiplied by 2 to the power of 2n minus n 4 to the power of n minus 1. This is equal to n 4 to the power of n minus n 4 n minus 1, which is equal to 4n 4 n minus 1 minus n 4 n minus 1, which is equal to 4 minus 1 n 4 to the power of n minus 1. And finally, we have this equal to 3 n 4 to the power of n minus 1. And so this is one way to prove this equality using the trick of this fundamental relationship between the union and the intersection. Now we can completely prove this equality another way. So the other way to do this is to write that the sum for A and B of the cardinality of the union is equal to the sum from k equals 0 to n of k multiplied by the sum for the cardinality of the union that is equal to k of 1. So we use the same trick as the intersection here. So we want to find the number of ways that the cardinality of the union of A and B is equal to k. So to count this, we start with the set E, and then we are going to choose k elements that represent the set A union B with k elements. And we know that there are n choose k ways to select this k element. Next, we are going to choose a subset that we are going to call A and contains p elements. And there are k choose p ways to select this p element among the k element. And now let's be careful because we want to choose another subset B, such as the union of A and B is exactly that set. So at least we have to select the set shown here. That is basically the set difference of A union B relative to A. And note here that we have only one way to choose this k minus p element. And finally, to complete this set B, that will be this one, we just have to select q element in the intersection of A and B, and they are exactly P choose Q way to select this Q element. So in other words, this sum will be equal to n choose K multiplied by the sum from K equals 0 to n of K choose P multiplied by the sum from Q equals 0 to P of P choose Q. We know from the binomial theorem that this is equal to 2 to the power of p. Similarly, we can show that this will be equal to 3 to the power of k. And so this sum will be equal to the sum from k equals 0 to n of k, n choose k, 3 to the power of k. As we have seen above, this is equal to n multiplied by the sum from k equal 1 to n of n minus 1 choose k minus 1, 3 to the power of k, which is equal to n sum from k equals 0 to n minus 1 of n minus 1 choose k, 3 to the power of k plus 1, which is equal to 3n sum from k equals 0 to n minus 1 of n minus 1 choose k, 3 to the power of k. So we just transferred one of the 3 from here to there. And again, by the binomial theorem, this is equal to 3n, 4 to the power of n minus 1. And so this is the second way to prove this equality.